We have already learned about the Euclidean algorithm as a way to find the greatest common divisor, or the GCD, between two integers that we call generically a and b. Well, there's an extension of this algorithm called Bézieu's theorem, which effectively allows us to do something with a and b and the corresponding greatest common divisor between a and b. So this theorem says that if we have these two positive integers, then there exist integers s and t. Now when you see there exist, that just means can be found. It doesn't say how, it just promises that if a and b are positive integers, then you can find integers s and t such that your greatest common divisor can be written as a result of a multiple of a plus a multiple of b. So we are hunting for these two integers that allow us to combine a and b, multiples of a and b, and end up with or equal to the greatest common divisor between a and b. Now I can give you a simple example of this. The GCD between 3 and 2 is in fact 1. We know that 3 and 2 are both prime numbers. The only number that divides both of them is 1. Now in this case you might be able to actually do this quite easily. Okay, the GCD 1 is equal to some number of multiples of 3 plus some number of multiples of 2. Now it just says there exist integers. Now remember, integers are written often as the set z, includes 0, positive and negative 1, positive and negative 2, and so on. So s and or t could be negative. Now it turns out that only one of them is going to be negative, but you can see here that I can't add positive multiples of 3 to positive multiples of 2 and go backwards and reduce the value down to a 1. However, if we think about this cleverly, we know that 3 minus 2 is already 1. And so if I apply a constant here of positive 1 and a constant here of negative 1, well then really what I'm doing is just 3 minus 2, which gives me 1. Now in this case, s would be equal to 1. That's the coefficient applied to whichever one we choose to call a. And then t would be negative 1, the coefficient of what we're calling b. Now this might seem like a trivial theorem, like, okay, well, if it's this easy for this one, it must always be this easy. But it turns out it's actually not the case. Let's consider two larger integers that we'll study here in a moment. The GCD between 296 and 124 is, in fact, if we went through the Euclidean algorithm, is 4. And let's try to answer the same question. To get 4, our GCD, we're going to take some number of multiples of 296 plus some number of multiples of 124. And now the task becomes much more difficult because, well, look at how far apart these two numbers are. And if I do 1 here and a negative 1 here, their difference is not the GCD. Here, it just so happened the difference between a and b was the GCD. So hunting for these multiples is not trivial. We could set up a little table where we pick a value of s, we pick a value of t, and then we see what the difference is between s times a, or I'm sorry, s times a plus t times b. We look at what that sum would be, and we could say, you know, okay, 1 and negative 1, well, that would simply be 296 minus 124, and that doesn't even get us remotely close, so that'd be 172. Now then we could try like 1 and negative 2, because that way you can see if I double this and negate it, that I'm getting closer to that difference, but 296 minus 2 times 124 is in fact 48. Okay, so that's still not close, it's closer, but I can't make this negative 3, because if I make that negative 3, well then this term, which will be negative, will surpass the size of this term, and there's no way we're going to end up with positive 4. So we would have to kind of keep on guessing, and this can get very tedious. And what we can't do is we can't just plug in a value for s and then try to solve for t using two-step equation because, well, for a given integer s, it doesn't necessarily mean that we end up with an integer value of t. So if I plug in a 1 here and then solve for s, I most likely will not end up with an integer value for s. I'll end up with some rational number. So it actually turns out that if you apply s to be 13 and t to be negative 31, well, now if you do 13 times 296 plus negative 31 times 124, this equation actually checks out. So the challenge that we have is, well, how do we strategically come up with 13 and negative 31? And that's where the extended Euclidean algorithm comes into play. It reverses the procedure of the Euclidean algorithm and takes advantage of what we've already written down to make our lives simpler. So next, let's go ahead and venture into the algorithm itself.